Hi everyone, in this video we're taking a look at question 8b part 3 of the New South Wales 4-unit HSC exam from the year 2000. So the very final part of the very final question on the exam. It follows on from part 1 and 2. And if you haven't already worked those out, I'd recommend going and taking a look at my videos where I work through each of those parts. So part 3 here says, by using induction on n is equal to r plus s minus 1, or otherwise prove that the probability of r comma s is equal to 1 on 2 to the power of n times, in brackets, nc0 plus nc1 plus all the way up to ncs minus 1 for s greater than or equal to 1. And we're given that or otherwise option, but I think I'm going to stick with the approach suggested, which is to use induction, where we're going to define n to be r plus s minus 1. And remembering for this question, r is the total heads, s is the total tails, and the probability of r comma s is the probability that you get r heads before you get s tails. Alright, so I might just start by writing up what we're being asked to prove so that we can refer to it. So we want to prove that the probability of r comma s is equal to 1 on 2 to the n times, and I'm just going to use nc notation here because that's what I'm used to. So it's going to be nc0 plus nc1 plus all the way up to nc s minus 1. And notice here that in this right hand side we've got s, we've got an s minus 1 but no r, so that's interesting. And then we've got this n where we define n to be equal to r plus s minus 1. So that's what we're going to work with, and we're going to follow the steps of induction. So step 1 of induction is to show that it's true for the first possible value, and in our case we're dealing with n, and because r or s can be 1 but and the other is 0, you can't have both being 0, but you could have one of them to be 1 and the other to be 0. If that was the case, you get 1 plus 0 minus 1 is 0. So we can actually have n is equal to 0. So let's show it's true for n is equal to 0, since that's the first possible value for n that we can deal with. So in that case, what we'd have is 0 is equal to r plus s minus 1. So if I brought that 1 over, we're basically dealing with r plus s is equal to 1. And the two ways that could happen is you could have r is equal to 1 and s is equal to 0. Or you could have r is equal to 0 and s is equal to 1. They're the two possibilities. Now, if r is 1 and s is 0, what that translates to is the probability of 1 comma 0. But you may remember from part 1 that that is equal to 0. The probability that you get a head before nothing else is not a possible option. So actually we can ignore this possibility because the probability of it is 0. So really we're just focusing on the case where r is 0 and s is equal to 1. Under those assumptions, does our left hand side equal our right hand side? That's what we want to show. So maybe let's start with the left hand side. So the left hand side would equal the probability of 0 comma 1, because we've got r is 0, s is 1. Now the probability of 0 comma 1 is equal to 1. That's the other thing we were told in the question. So it's kind of now clear why we were given those two little steers. They're helping us in this induction. So okay, the left hand side is 1. What does the right hand side simplify to? So let's have a look at the right hand side, which would be equal to 1 on 2 to the power of 0, since n is 0, times nc0, and we don't really go any further because we've got s is equal to 1 and 1 minus 1 is 0, so nc0 is both the first and last term, so that's all we need. 2 to the 0 is 1, anything to 0 is 1, so this is just going to be 1 on 1 times 1, and that's because nc0 is equal to 1. Any number combinatorial 0, and anything c0 is 1. So 1 divided by 1 times 1 is 1, and that's the left-hand side, since we worked out, or we were told basically that that's 1. So therefore it's true for n is equal to 1. So that's, n is equal to 0, our first possible value of n. So that's a good start for the induction. We've got our step 1 covered. So I might just turn over and we'll do the step 2 of the induction, which is to assume true for n is equal to some integer k. So if that's the case, what we're saying is that the probability of r comma s is equal to 1 on 2 to the k, since we've got n is equal to k, of kc0 plus kc1 plus and so on up to kcs minus 1. So we're going to assume that's true and then hope that we can make use of it in step 3. And step 3 is to show that this relationship is true for n is equal to k plus 1. And this is where the hard work typically comes with any induction question. So, just like before, just like with step 1, we want to show that the left-hand side will be equal to the right-hand side. And we're going to anticipate that in that process, we're going to make use of this assumption. And that's going to get us through to the induction. So I think in this case, it might be easier to just start with the right-hand side and throw in a k plus 1, because that's going to be simple enough. So the right-hand side would be equal to 1 on 2 to the k plus 1 times k plus 1 c0 plus k plus 1 c1 and so on up to k plus 1 cs minus 1. So that's the right-hand side, and I think the real hard work is going to be to show that the left-hand side can simplify to that. So the left-hand side is the probability of r comma s. That hasn't really changed. Now I think it's going to be helpful for us to make use of our result in part 1, and this is where the scaffolding of the question becomes relevant. I think we can make use of that relationship where all the way back in part 1 of this question, it's part 2, so part 1 we were asked to show this result here. And so I think we can make use of that. So it's a half p r minus 1 s plus a half p r s minus 1. So let's throw that in. So this will be a half p r minus 1 s plus a half p s r minus 1. R s minus 1. So that's the part 1 relationship, and why I think that's interesting or helpful is because this p r minus 1s and this p r s minus 1, well, we can link that to our assumption in step 2, because remember, as I noted earlier, r isn't anywhere here in this this right hand side here. So whether it's r minus 1 s or r s minus 1, we can just write the same thing, and it all just comes down to where do we stop, and it's whether we've got an s or an s minus 1. So we can write this as a half times the probability of r minus 1 s, making use of what we assumed in step 2, we can write as 1 on 2 to the k times kc0 plus kc1 and so on up to, well, if this is s and this is s, we'll keep going to kc. I might just write the last two terms, s minus 2 plus kcs minus 1. That's kind of where we stop. And then we've got this bit here, so we've got plus a half times, and we do it again, 1 on 2 to the k times kc0 plus kc1 and so on. But here, because we've only got an s minus 1 here, we're going to stop at s minus 1 minus 1 or s minus 2. So plus kc s minus 2. And so that's why I wrote that second last one there, to make it really clear we've just got one extra term in here. And I should note that the result that we had in part 1, I don't know if I wrote it down here, but the question did note it's for r and s greater than or equal to 1. So really, actually, what we're showing in relying on that result, what we're showing here will hold true for, in particular, r greater than or equal to 1, I think is the main point, because we're then going to have to separately show that the left-hand and right-hand side is true for r is equal to 0 too, so that we're covering all our possibilities. So that's an important caveat. I think if we don't note that in the exam, you'd probably lose some marks because you haven't shown the complete picture. I think if you can get through this, you get a lot of marks, but not all of them if you don't then do that extra step of showing it's also true for r is equal to 0. So we'll do that later. We'll finish off this process. In terms of simplifying this left-hand side, we can certainly factor out this 1 on half times 1 on 2 to the k. And given we want to get a 1 on 2 to the k plus 1, I think it makes sense to bring this 2 and 2 to the k together, because that will give us 1 on 2 to the k plus 1. So we'll have that factored out. And now I'm going to write this in a very deliberate way. We're going to take our kc0 from up here. And then I want to link these kind of offset terms. So there'd be a kc2 there if you imagine it. And then in particular these two. We're basically adding up kind of the offset items. So here it would be this kc0 plus the kc1. And then we get our kc1 plus kc2, and so on. We'd keep going, and we'd end up at the end with a kcs minus 2 plus kcs minus 1. So that's kind of what we're dealing with. And the reason I wanted to write it in these pairs is because hopefully that then kind of hints at you that there's a certain result we can make use of. So you may remember that we've got basically one of the results from Pascal's triangle. So we can note that it's true that NCR, and you actually learn this in 3 unit, but obviously 4 unit people would be expected to know it too, is equal to n minus 1 CR minus 1 plus n minus 1 CR. That's one of the identities that you'll learn. Now, we're kind of looking for k plus 1s here. So actually, this result would be more helpful if we kind of add 1 to all of these. So you'd end up with n plus 1 CR is equal to n plus 1 minus 1, or n CR minus 1 plus NCR. And this result, you can kind of see we can make use of, because we can say, therefore, we could say kc0 plus kc1. Well, what would that be equal to? Well, in our case, we kind of think of the n's as the k's. So we're going to end up with a k plus 1 c, and you pick the r, so the higher of the two, so the 1. So this kc0 plus kc1 will be k plus 1c1. The kc1 plus kc2 will be k plus 1c2. And there's probably enough room to write the last one, which is the kc s minus 2 plus kcs minus 1 would be k plus 1 cs minus 1. And so now we've kind of simplified all these. I'll definitely have to turn over now to say, therefore, our left-hand side is equal to 1 on 2 to the k plus 1. That's what we had factored outside. Our kc0 plus this we can replace with k plus 1c1 plus a k plus 1c2 and so on, all the way up to our k plus 1c s minus 1. Now, if we take a look at this, we are super close to the right-hand side because k plus 1c0, k plus 1c1, we've got that. It's just this k plus 1c0 that's an issue because we don't have k plus 1c0, we have kc0. But you may remember, I think I made use of it somewhere. Oh yeah, here. nc0 is equal to 1. Anything c0 is equal to 1. So kc0 will be 1. K plus 1 c0 will be 1. So actually, for this first term, kc0, I could write kc0. I could write k plus 1 c0 because they're the same. They're both 1. So actually, I could write this as 1 on 2 to the k plus 1 times k plus 1 c0 plus k plus 1 c1 and so on, all the way up to k plus 1 c s minus 1. And there, that is our right-hand side. That is exactly what the right-hand side becomes when we assume n is equal to k plus 1. So we could say, therefore, true for n is equal to k plus 1 and r greater than or equal to 1. So I think we've done a lot of the work, but not all of it, because now we need to do the same thing, but we need to say if r is equal to 0, do we also get our left-hand side equal to our right-hand side? So if r is equal to 0, what are we really dealing with? Well, remember we've got n is r plus s minus 1. We're in step 3, so n is k plus 1. So we're going to have k plus 1 is equal to r, which we're saying is 0, plus s minus 1. So really what that means is when r is equal to 0, s is equal to, we'll bring the minus 1 over, so k plus 2 is what we're dealing with. Okay, so, okay, well, what is the right-hand side? I think it makes sense to start with the right-hand side again. So the right-hand side would become 1 on 2 to the k plus 1, because we're still in the territory where n is k plus 1, so n is k plus 1, times k plus 1 c0 plus k plus 1 c1 and so on, up to k plus 1 c, and here's where s becomes relevant. It's s minus 1, and here we've got s is k plus 2, so s minus 1 would be equal to k plus 2 minus 1 or k plus 1. So this will be k plus 1c, k plus 1. Alright, so that's the right-hand side. Now, I think we can do a binomial expansion here, because I think this bit here, we can make use of the binomial expansion result to simplify it. So note in our binomial expansion, in general, we know that x plus y to the n can be written as the sum from k is equal to 0 to n of nckx to the, and there's a few ways you could write this, it almost doesn't matter, but for our case, n minus k y to the k. The reason I say it doesn't matter is we're going to let x and y both be 1, because I want 2 to the power of something, so we're going to get 1 plus 1 is 2. So if x is equal to y is equal to 1, then what do we get? We get 1 plus 1 is 2 to the power of n is equal to the sum from k is equal to 0 to n of nck 1 to the n minus k times 1 to the k. 1 to the anything is just going to be 1. So this simplifies to nc0 plus nc1 plus and so on, all the way up to ncn. Now if we take a look at that, we can say, well, therefore, if I just replace all the n's with a k plus 1, 2 to the k plus 1 is k plus 1 c0 plus k plus 1 c1 and so on, up to k plus 1 ck plus 1, and that's exactly what we've got in these brackets here. And so that's why it's going to be helpful, because therefore our right hand side becomes 2 to the k plus 1, this bit here, divided by 2 to the k plus 1, which equals 1. So we've got our right hand side simplified to 1. What about our left hand side? So I might have to turn over. Our left hand side is equal to p of, left hand side is p of rs. Now remember, we're in r is 0 territory. So p of 0, comma, and s we worked out is k plus 2. Now what is this? Now you may remember in, I think it was the video for part 1, I talked about this a little bit. I touched on it because we were told that p of 0, comma 1 is equal to 1. And I mentioned that actually this is going to be true for any value, k plus 2, 1, just n. You could put n in there and it's going to be a probability of 1. And what I might do is I might flesh that out, show it, so that we can say the left hand side will be 1, and that's equal to the right hand side, which we just worked out was also 1. And I think maybe what I'll do, let's just do a little side note. P of 0, comma n is basically saying we're going to get no heads before we then get any number of tails. So how can we do that? Well, it's going to be the probability that we get no heads and then 1 tail, plus the probability we get no heads and 2 tails, plus the probability we get no heads and 3 tails, and so on, like just keep going forever. And so, well, what is this? Well, the probability of a tail is a half. The probability of 2 tails is 1 on 2 squared. And the probability of 3 tails is 1 on 2 cubed. And I'm deliberately keeping it like this, 2 to the 1, 2 squared, 2 cubed, and so on forever, because that is the sum from, I'll just pick k, it's probably not the most helpful letter, but k is equal to 1 to infinity of 1 on 2 to the k, is how you might see this style of thing written out. Now this is an infinite geometric progression where we've got our first term, a, is a half, this one here. Our common ratio is also a half, each one's growing by a half. And you may remember the sum of an infinite GP is a on 1 minus r. So this sum here would become a, or a half, on 1 minus a half, which is a half on a half, which is 1. And actually this is an example of something called Xenos Paradox. I don't know if you've ever heard of it. I don't think you officially learn it in the syllabus in New South Wales, but you know, basically, you know, what if there's a few ways you may have heard it described, like what if a frog always jumps half its prior distance, where will it get to? Or what if you've got a full tank of petrol and you, not even petrol, what if you want to get somewhere and you decide to always just go halfway there first? Do you ever make it? Well, the answer is yes, you get there. It'll add up to 1 if you're thinking about it as an infinite GP. So anyway, if the probability of 0, comma any integer is 1, we can therefore conclude that the left-hand side is equal to the probability of 0, comma k plus 2, which is equal to 1, because, you know, for any integer it's 1, and that's equal to the right-hand side because we just showed that was 1. So, therefore, it's true for n is equal to k plus 1 and r is equal to 0. So we've covered all our bases now. We've covered r is equal to 0. We've covered r is greater than or equal to 1. So we're good. So I think it's just now that final step of the induction, which I won't write out all the words. I think different teachers probably teach different disciplines here. I'm just going to say by induction and leave it to you to follow whatever way you were taught. But by induction, we can say that the probability of r comma s is equal to 1 on 2 to the n. And I just want to make sure I write this properly at the final step. 1 on 2 to the n, nc0 plus nc1 up to ncs minus 1. So nc0 plus nc1 plus and so on up to ncs minus 1. Boom! And that's that question done. So certainly a lot of work there, a lot of possibility for error. Certainly I think where the bulk of the marks are probably going to be allocated in this question. You really need to have had a pretty good understanding of what was going on with this question. Like, what is PRS? What is the deal there? I think part 1 and part 2 kind of scaffolded it in and got us to think about it a little bit. But then we really had to make sure we were all across it to get through this induction. I think showing true for n is equal to 0, that was probably simple enough. And then obviously step 2 is always easy. But step 3, I think realizing or linking it up with part 1, but noting that there's a restriction there. You know, using these Pascal's results to simplify this. I don't think all students would necessarily get their head around that. And then, you know, remembering to do it for r is equal to 0 and making use of this binomial expansion. I think a lot of students would probably just miss that altogether. And then, I guess finally this whole Xenos Paradox bit where we're able to demonstrate that it's not just P01 that's equal to 1, it's P0n for any number, and therefore we can get P0k plus 2 to be 1 as we needed. So yeah, I think a lot of tricky bits in there, but hopefully despite all that you were still able to follow along and it all made sense. And tick boom.